Because all of those protons and neutrons exist, we can get a couple different numbers from them. Okay, numbers from them, sorry. We have what's called an atomic number and what's called a mass number. Now I have in underlines up here what they are, okay? And again, being able to pick this out of a multiple choice, or a matching, obviously that would be the way to go about doing it, right? But the atomic number is equal to the number of protons, okay? So if you were asked on an exam what the atomic number is representing, it would represent the number of protons, okay? So let's say the question said there are, 6 protons, 6 neutrons. What's the atomic number? And you would say 6, okay? Because it's the number of protons. Mass number is equal to the sum of everything in that nucleus, okay? So the mass is what is within the nucleus, the totality of that nucleus, okay? So everything in there has mass, all right? So mass is the entire number. The atomic number itself is just protons. So that's the difference between them. Obviously, because there's one word difference, people flip-flop this around on an exam, okay? Your atomic mass unit, okay? That's approximately equal to the mass number. Okay. I don't have a lot of space on these slides, how I devise them. I don't like that. Let's see here. So let me do this. For the atomic mass, the thing to remember here is that it can change over time, right? There are different publications, there are different groups of scientists, and they will revise what is the value of an isotope, okay? And we'll get to what an isotope here is in a second. So an atomic mass number can sometimes change depending upon the lab. That's all I want to say. This is okay. The atomic number is going to be the value that is usually associated with the element within the periodic table. Okay. This is key to identifying. This is a key thing to identify this element, is this atomic number, because it's giving you the number of protons, okay? Because isotopes exist. Isotope is the same thing, just a slightly different proton number, okay? Carbon 12, carbon 13, carbon 14. Hydrogen exists in a few different forms, H1, H2, H3, right? These are all due to the slightly different number of protons, right? They're all basic hydrogen, but because they have a different proton, they have some different chemistry that's associated with them. So that's why we talk about these numbers here, all right? So atomic number, mass number, and atomic mass unit, all right? Being able to differentiate these on an exam, always a good thing in either multiple choice or matching. There's plenty of good short answer questions. This doesn't necessarily make a good short answer question because I got other ones for that. And when you look at a periodic table, okay, that's what all these numbers are. Okay? Mass number, atomic number, and that atomic symbol there. When you look at a periodic table, when you're trying to figure out what everything is, you'll see that they are arranged in rows called periods, and they are arranged in columns, and those are called groups, right? The great thing about the way that this is, it goes, you know, as it goes across, it gets heavier and heavier. There's a greater atomic mass. But when you look up and down, groups share characteristics. So everybody here in this column all reacts the same. Okay? Everybody in this column will all react the same, yada, yada, yada. All right? So that's the great thing about kind of putting these within these different groups. Okay? From a chemistry standpoint, you can figure out how they all kind of interact with one another, or how they all respond in a chemical reaction. Here's isotopes. Okay. Again, same element. It's still carbon, still carbon, still carbon, but they differ within their number. I'm sorry, neutrons, not protons, neutrons. Okay. You see the proton number staying the same. Okay. It's the number of neutrons that is varying. This is great because now I can figure out rates of decay. I can measure things. I can make something that gives off a little bit more radioactivity, and I can use that to date stuff. That's what carbon-14 is. Okay. I can manipulate an element, and I can make it to where it gives off a little bit more energy, and I can make an image. Okay. And that's what we have here. Okay. Where we're doing various different types of PET scans, CTs, you know, not necessarily a bone scan, okay? But here I can do positron emission tomography, and I can utilize isotopes that give off a specific type of radiation when I inject them into a structure. And you can see some activity, some enzymatic activity, some metabolic activity in structures here in the thyroid, to determine if it's overactive, here within the brain to kind of see what's going on inside the brain, the brain activity there. I can do it to treat cancers. I can do it to treat fruit. You can blast fruit with a little bit of low-level radiation, and you can kill the bacteria that are on the surface that have occurred after you've plucked it off the tree and handled it with I don't know how many people handling it. I can blast it with a little low-level radiation, and I can prevent spoilage, okay? Killing the bacteria on the surface, killing all the bugs that may be on it that you can't see with the unaided eye. Or hell, even a handler handling it who didn't maybe wash their hands properly. Right? You can eradicate that stuff on the surface, and it allows it to be traveled and transported around, because food can be grown all year round. Bugs are different at different times of the year. So, I mean, you can treat food, not necessarily fruit, but food with some low-level energy and radiation, okay? And you can get rid of some nasty little microbes on their surface. So we have the nucleus where we have our protons and our neutrons, and we have floating around it those electrons in these little bitty orbits. There's a specific model that it's called the Bohr model. That's the way we kind of visualize the location of electrons. And this is an important thing to remember. Electrons, even though they don't really have any weight to them, any significant weight to them, they do have energy within them. And that negative energy, it takes energy to hold those things in place. Okay? Just like gravity, the pull of the sun keeps all of the planets in their orbits. The same concept here. Okay? That nucleus, think of it as the sun. And it's exerting a force to both, basically to keep those in. Okay? We want to keep them in the right spot, so it's going to exert a force out. Okay? But those electrons are going to be attracted in, and it's this opposing type of forces that are occurring in this nucleus that hold these, I'm going to go forward a slide, okay, or two, that hold these electrons in this specific little orbit. Okay. Holding these two electrons in this orbit, and they don't move. Okay. These things are attracted here to this, and this positive thing is going to exert a little force and keep these little bitty nuggets of electrons right there. All right. Then you can see we have another shell, another orbit. Okay. And we have electrons here. Okay. These are going to want to go in, but these are going to be repelled by these guys here. They're pushing out. They'll be like, hey, this is my space, and don't come in my space. And you can kind of see as we go up, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Do we see a theme here? Hydrogen, 1, 1. Okay, it's kind of the outlier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got the number of protons equaling the number of the electrons here. Okay, so this number also tells you the electrons as well, by golly. These electrons just floating in these orbits are just floating in the orbits. Okay? But they have energy with them. And this energy that these guys have inside of them, energy inside, has a potential to do work. Potential. Okay. Potential to do work. Okay. And you guys know that. That's called potential energy, PE. Okay. So they have the potential to basically help make energy. Okay. It's the presence of these electrons that determines how these things react with other elements, how they react with each other. Okay. And we'll see this concept of electrons in the next unit when we talk about energy, okay, and the energy within these tiny little nuggets, and how we can actually harness those things that have a lot of potential and get something out of it. Right? That's the hallmark for photosynthesis. That's the hallmark for metabolism, cellular respiration. All of it found in these tiny little things floating around. Okay? They have the potential. They have the potential. And as I remove, I can harness that energy for me to make energy, to do stuff. The model that I'm just looking at on that slide is called the Bohr's model. All right, that's the model that we use to kind of visualize where these electrons are located. These orbits have various different names. And again, I don't really care 2 bits if you know them. All right, I want you to know some basic rules. Do I have it? Yeah, it's on the next slide. Okay. Electrons in the first shell, because there's several shells, several orbits. Shell equals orbit, okay? I'm going to be using them interchangeably. I apologize. I'm sorry, but that's just how it rolls, all right? Within each shell, which within each orbit, okay, the further we get out and out, the more greater the amount of energy that we need to do to hold these suckers in, right? Because they're real far away, so I have to exert a lot more pull on those to keep them here. In the first shell, it can only hold 2 electrons. In every shell after that, each shell after that, it can now hold 8 electrons. This little nugget of piece of information here will allow you to figure out if we have bonds that take away, like an ionic bond, or if we're going to have bonds that can potentially share. Okay, and those are covalent bonds. All right, so this little concept here of filling a shell before we get to the next one is important. If I go ahead a couple slides here and look here, okay, here we go, that first shell right here. Okay, there's the first shell. Shell 1, shell 2. 1, 2, 1, 2, 1, 2, 3. 1, 2, 3. Okay, and we can add another one. But you can see that first shell, it only needs 2 electrons. There's one. It has another spot here. Okay, there's an open vacancy right here. So it's going to want to react with a lot of things. Okay, it's going to react very easily. But I can't add another shell. I'm just going to dot another shell here. Okay, I can't put any electrons here until I put somebody in that first shell. And that's what you see, right? That is what you see right here with carbon. Okay, got an electron, fill in another electron. Now I can add more. 2, 3, 4. And remember, anything after the first shell loves the 8 number. Okay, so we have 4 vacancies on carbon. Carbon can react with a lot of stuff and form a lot of various bonds because it has 4 openings. So it's very reactive as well. The nitrogen, what does it have? It has 7. So how many is it going to need? Okay. In that outer shell, what do I have? 1, 2, 3, 4, 5, 6, 7, 8. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. In this outer shell, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can figure out how many potential bonds this thing can have just by looking at that outermost shell. And again, that will give you a pretty damn good idea on if these things are going to be ionic or covalent type bonding with other creatures, okay, with other atoms, with other elements. That outermost shell is referred to as the valence. The valence shell determines these properties of how this thing is going to react. How chemically reacts with others. Okay, with other elements. This rule of 8 is referred to as the octet rule. And every shell, except for the first, wants 8 electrons. Okay, it wants 8 because that's most stable. Okay, elements like to be stable. Excuse me. If they're not stable, they're reactive. Okay, When they're stable, no reactions. Okay, it's not going to bounce around and find stuff. Oh, haha, let's react. Boom. I'm bouncing into stuff and do a reaction. Okay, once it's got its octet rule, it is happy. Unless we have signals like within the body, chemical signals that say, hey, you need to go over there and you need to do stuff. Okay, then that element's going to go over there and do stuff and yada, yada, yada. We're going to lose an electron. Okay. And now it's going to be like, okay, where's my dance partner? Where's my dance partner? I need to react to somebody. And goes out and reacts. Right? Where in the hell would you see this in the human body? Well, pretty easy. Any type of metabolic reaction. Any type of reaction in the body is going to produce some kind of element that is going to lose an electron. And it's going to be like, I got an opening. I'm not right. I need to react. And it's going to want to react to something. Okay. We give them another word though, within the body. Okay. In the world of nutrition anyway. We call these things free radicals. And free radicals have an opening. And they don't like having an opening. And so they'll go and react with anything that they want. And that spells doom for tissues. Because if free radicals accumulate, well, they'll cause wear and tear in structures. Look at your skin. Okay? If you expose the skin to a carcinogen, like when you smoke, okay, that causes enzymatic reactions inside because the body's trying to handle all that carcinogen. Well, you get an accumulation of all these free radicals. Those accumulate in the skin. That starts to wear down those collagen fibers, and then that person looks really old. All right. So this concept of the octet rule and having 8 and being 8 as being stable, and if they lose one, then they're not stable and want to react with somebody. Okay, that's why this is important. Okay, because this is the basic understanding of how aging happens, how wear and tear happens. Okay, it's the accumulation of these free radicals. A good diet helps to limit that and reduce it. Okay, but that concept of free radical accumulation when it comes to, exposing yourself to carcinogen, eating like crap, not getting enough sleep, any of those things can cause the production of free radicals. Okay, stress can cause the production of free radicals. Okay? And it's these free radicals because they have an open spot. They're not subscribing to that octet rule. Okay, they've had something plucked away because of a weird enzymatic reaction. Now they're looking to react with anybody. And that's what breaks down cellular structure. Okay, it is that valence electron, and it's in underline there. Okay, it is that valence electron that determines whether it's going to accept or whether it's going to share an electron to acquire the 8. All right, because we want to appease that octet rule. We want to be chemically stable. Again, like I said, if they're not chemically stable, they're reacting. And that's not a good thing. Or it's potentially not a good thing. Chemical reactions are fine. Okay? You need them to go. It's just that sometimes they give you stuff that you don't like free radicals. So I got all these elements willy-nilly moving around, okay, within the ether here. All right? They're bouncing around, they're interacting, they're forming stuff. Okay? When two elements kind of come together there and form structure or form a more complex structure, that is referred to as a molecule. Okay, 2 or more, 2 plus, bonded together. Okay, look at my examples here. Sodium and chloride. First letter is always capitalized, second letter is always lowercase. That's how you know. Okay, and then there's 2 elements there, right? 2 different elements. Okay, sodium and chloride. What else do we have here? We have 2 hydrogens. Okay, 2 hydrogens. Hydrogen and hydrogen. Okay, that still gives us 2 elements. Does it say anything in that definition that they have to be different? No. So a molecule, 2 or more elements bonded together. Excuse me. And they can be the same. Okay, they can be the same. What separates a molecule and a compound is that minutia. Okay, a compound contains at least, again, 2 elements, but we put the moniker 2 different elements. Okay, it is the difference in one word that changes you from getting an A to a B, okay, or an A to a C. There's a lot of these questions, and I ask a lot of these questions. Science is based on one word being different. So when you're taking these quizzes, when you take these exams, read the whole question, okay? Make sure you read the whole question. Make sure you read the entire distractor, the entire choice, because there's going to be, you're going to whittle them down. And you're going to be like, I don't know this answer, but I know it can't be this one. And I know it can't be that one because they are related to 2 totally different other concepts. So I have 2 choices now. And it's going to be, they're going to look pretty damn similar, and they're going to be one word different, all right? And this is a great example of that concept where I ask questions like this. A molecule is 2 or more elements bonded together. They can be different. They can be the same. For a compound, at least 2 different elements that are different. Okay. 1, 2, carbon and oxygen. As you can see, there's 2 oxygens. Okay. We have a carbon, and I have an oxygen, and I have an oxygen. H2O. 1, 2. 2 different elements. Okay. Even though it's three, 6 carbons, 12 hydrogens, 6 oxygens. We have at least 3 different here. Okay, so the difference between molecule and a compound is that minutia, that one word difference. Molecule, 2 or more elements bonded together. Compound, 2 or more different elements bonded together. Don't screw that up. Then formula is just, tells you what's in there. Okay, 1 carbon, 2 oxygen, 2 hydrogens, 1 oxygen, 6 carbons, 12 hydrogens, 6 oxygens. Okay, so the numbers tell you. All right, so we have these electrons floating around in various different shells. Okay, that outermost shell is going to be our reactive shell. It's that valence shell. Okay, and those are valence electrons floating around in it. So those are going to be the dudes that are wanting to play around and react. These electrons floating around there and the number that they have there will determine basically what type of chemical reaction or what type of chemical bond will form from the chemical reaction. To that end, we have 3 major type of bonds that result from chemical reactions. We have ionic bonds, we have covalent bonds, and we have hydrogen bonds. Okay, those 3. Would they make a great short answer question on an exam? You betcha. Okay, being able to describe these things and give an example of these things would be a fantastic short answer question on an exam. Okay. The first one we have here is an ionic bond. An ionic bond takes. Okay. For me, I visualize this. Okay. I have 2 sides of the wall. To get from one side to the other, okay, this guy's got to take himself all the way to the other side. Okay. Got to get around that fence. Okay. So with this one, I have electrons are transferred from one atom, okay, and attached to another. Let me just go over here. So here's my one shell, okay? Here's my two shell, and there's my third shell. 1 and 2. Appease the rule, right? The first shell always has 2. Then I look at the next one, the second shell. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule satisfied, right? So let's put the next one out. 1. Okay, 11 electrons. Is the octet rule satisfied here in this outermost shell, this valence shell? Of course not. We've just been talking about it, and you are fully confident in your knowledge right now. Well, let's look at chloride. 1, 2, satisfied. 1, 2, 3, 4, 5, 6, 7, 8, satisfied. 1, 2, 3, 4, 5, 6, 7 in that outermost shell. So what do you think? Chloride takes it. Sodium gives it up. Chloride takes it. And these guys come together. And there you go. Now, remember, what are electrons? Remember, electrons are negative, right?
Question.
Yeah.
Can you just repeat, like, can you explain the chlorine taking that again? I kind of lost you.
Sure. What do all of these shells want? They want that octet rule, right? How many does it have? How many does sodium have in that outermost shell? It just has 1. If we look at the outermost shell over here, what do we have? 1. Damn. 1, 2, 3, 4, 5, 6, 7 electrons. So what does it need for the octet rule? For the octet rule?
8.
It needs 8, right? So it needs that 1 more, right?
Yes.
So it's going to bind with something and take its electron. Sodium will come over here and bind to it. It'll take this electron. Okay, it'll come over here. When you look at this thing, then these two kind of congregate closer together here. All right. Now, up here, that's what I just drew on the previous slide. All right. Now down here, these two guys stay close together. Okay. Opposites attract, right? Likes repel. So here, sodium and chloride, these two ions, stay close to one another here because they now have opposite charges, right? Because electrons are negative, right? When I lose an electron here, when I lose a negative number, it becomes more positive. Does everybody see that? If something's -1 and now it becomes 0, it's become more positive. Conversely, if I gain an electron, it becomes more negative. So that's why the chloride ion is written like this, Cl-. Octet rule is satisfied. Okay? Chloride ion isn't going to go play around with anybody else now. It has its partner, sodium. Okay? They're very close to one another. And as you can see how a visual representation looks like, there it is right there. Forms a nice kind of rigid structure. And you know it as salt. Okay? NaCl is salt. It's coming together of these two ions, and you can kind of see, there they are. Okay? Negative, positive, negative, positive, negative, positive, negative. All of those positives and negatives are attracted to one another there, and they form these cube-shaped orientated structures here. And that's what you see right here in crystals. And that's what we see right here in salt. Okay. So salt is an example of a structure that forms from ionic bonding. Now, can I get salt to react? Yeah, right. You've dumped salt in solution before, into water before, and it dissolves. We break it up because I've destroyed those bonds. Okay, and now I can separate the ions out again. What is an ion? I keep saying that word. It's something that has lost or gained an electron. It can be positive or it can be negative. Okay. So our first type of bond, ionic bond. Ionic bond takes, okay? One ion takes it from another. One element takes it from another, becomes an ion. Okay? The one that gains the electron becomes more negative. The one that loses it becomes more positive. Why does it become negative? Why does it become positive? Because you know from the beginning of the lecture, electrons are negative. Okay? We will see this phenomena a lot in the next unit when we talk about metabolism, photosynthesis, cellular respiration. Okay? So we will be using this concept again, okay, of becoming positive and negative. Our second type of bond is a covalent bond. And for me, I always visualized it like this. Okay? The two ends, my electrons, okay, are connected to one another. Okay? So they're sharing the love. Right? Covalent bonds result when the two atoms share electrons. Okay? When the two atoms share electrons. They can share them equally. They can share them unequally. Ionic bonds are ionic bonds. There's no subdivisions at all. Okay? But when it comes to covalent bonds, we have a number of covalent bonds that are nonpolar. Okay? Where everything is shared 100% equally. What does that look like? Here are some examples on the next slide. On the next slide. Okay? They share them equally. Okay? They'll go here and they just kind of go around and they share them equally. Okay? Sharing equally. Sharing equally. How do we know that? Math and a bunch of chemistry that we don't care about. Okay? As you can kind of see, it can be written in a multitude of ways. You can have a single bond. You can have a double bond. Okay? And you can even have a triple bond as well. Okay? Strongest. Dang. Strong. Yeah, okay. Okay. Yeah, some okay strength. All right. But these are my nonpolar covalent bonds. Okay. Everybody shares equally. Okay. And this is hydrogen gas. This is H2 on that slide that we were just at. Okay. Oxygen gas, O2 that we just had over here. And methane is CH4. Okay. And again, all those are examples are right here. Electrons are being shared equally between the two atoms. Okay? Nonpolar. We also have covalent bonds that have some polarity. Now, polarity just means, let me just write this down here. Polarity. What is polarity? Okay. Polarity is just a separation of an electric charge leading to a molecule or to its, chemical group. All right. All of these here, if I go back one slide, as you can kind of see, they're all kind of equal in their shape. Okay. This angle and this angle and this angle and this angle is all the same. That angle and that angle and that angle and that angle are all the same. The same. The same. When we come to polarity, okay, they share them, but they share them unequally. Okay. This is referred to as electronegativity. This is the hallmark, and damn, we're going really slow. This is the hallmark for what water is and what water does for us. Okay. So they share them unequally. Polarity means they have a charge. Okay. They have a charge. One end is more positive, one end is more negative. What does that look like? Here's what it looks like. Okay. This is referred to as a dipole. Okay. Dipole. D-I-P-O-L-E. Okay. We have one end that's more negative, and we have one end that's more positive. Okay. And as you can see, this angle here is much different than this angle here. Okay. So this tells you that they're not sharing them equally. This is fantastic. Okay. This setup's fantastic though. It allows this thing to interact differently with different things. Okay. It can make bonds. It can make, damn, there we go. It can make a bond with something over here that's more positive, like another hydrogen atom. And another hydrogen atom. And an oxygen atom. And then there's hydrogen and there's hydrogen. Okay. So it can make a whole multitude of various different reactions, okay, or chemical bonds with other things because of this non-equal sharing here. So ionic bonds, one takes from the other. Covalent, they share. They can share equally or they can share unequally, okay, kind of like my kids. I won't play it here, okay, but please watch this video. It's a nice little short little video. You should be able to just click on it, click play when you open it up in the PowerPoint presentation, okay, and watch it and review it, and I'll talk about the same stuff that we talked about here. The last bond that we're going to get into before we get into the properties of water, and we just might make it, we're going to make it today, okay, is this thing called a hydrogen bond. Okay, so we have ionic, we have covalent, and we have hydrogen bonds. Hydrogen bonds are weak mothers, okay? Weak, 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 weak. By themselves, hydrogen bonds are weak, 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 weak. But you put a bunch of them together and they're really strong, okay? How do you know that? Well, I mean, you've taken your hand before and you've hit the surface of water, right? You've belly flopped before, okay? All that hand surface, all that surface of your belly smacking all that surface of the water, man, that hurt like hell, right? That's hydrogen bonding, okay? Holding all of that surface tension together. But, you know, you reduce the amount of surface that's interacting with each other and you dive in, okay? Or take your hand and go in straight down, and now it just, boop, just goes right in the water, right? Again, fewer hydrogen bonds are interacting when you dive in the water like that. So the force that you hit that water with, you don't really notice it. as opposed to belly flopping. All right, more surface hitting more water surface. All right, so these hydrogen bonds. It is these hydrogen bonds that make water such a unique thing. Okay, water is a polar molecule. Its shape is dictated by. There we go. Its shape is dictated by that non-equal sharing from that covalent bond, that polar covalent bond. All right. These hydrogen bonds allow water to do what it do. These hydrogen bonds allow DNA to form its structure. Okay. This concept of hydrogen bonding is how complex proteins form. What's a complex protein? Hair is a complex protein. The stuff inside the hair is a complex protein. All right. So it is this weak, really, singular hydrogen bond, but when you get a bunch of them together, man, it allows so much to happen and allows so much to occur. I can make these super complex structures like hemoglobin in your red blood cells, okay? Like collagen fibers, keratin fibers, okay? I can make complex protein structures because of these hydrogen bonds. So even though they're really weak as heck, man, they do so much in the world of biology that gives shape and structure to all of the various things that we talk about throughout. Another great video for you to watch. Please watch it. It's in there for you. PowerPoint presentation mode. Put it on. Hit the play button. All right. And here, this shows this electron model here, okay? The Bohr model of it. Okay, here you can kind of see the unequal sharing there. Okay, different angles. But here you can see those dotted lines are drawn in representing a hydrogen bond, and you can see the positive is orientated towards the negative, negative orientated towards the positive, positive orientated. And it is this interaction that allows water to have so many fantastic, unique properties that allow life to really occur. Colton, you bet. Okay, and we're going to see, what this all does, because as water can change states, the amount of distance between these hydrogen bonds can change. And when water becomes solid, the hydrogen bonds are pushed out a little bit because water is now frozen. So that pushes out the elements away from each other, these molecules away from each other, right? And that hydrogen bond extends further out. So it's a little bit weaker. So now it becomes lighter in the process. And that's one of the characteristics of water. There are 1, 2, 3, 4, 5 properties of water that would make a great, that would make a fantastic, that would make a stupendous short answer question on the exam. If that's not a hint, I don't know what we can do for you, okay? The water molecules are all clean together, again, because of those hydrogen bonds. So the very first property of water, number 1, it has a high heat capacity. Water has a high heat capacity. It's because of these hydrogen bonds, okay? Those hydrogen bonds can absorb a large amount of energy, heat, okay? So the temperature of water rises and falls slowly. It takes a long time for water to boil. Yes, you've all boiled water before. If I apply that heat to it, should it just initially just all of a sudden start up? And you would think so, but it doesn't, okay? It takes a while. The higher the heat, the faster the ability to heat it up, okay? The less the heat, the longer it takes to heat it up. It is that hydrogen bonding there that is absorbing that energy, that heat. All right, so it allows water temperature to rise and fall slowly. That's awesome. Okay, when it's really hot outside, you don't want all the water boiling off, and all of a sudden we're left without any water on the planet. That would be stupid. Okay, but not just from maintaining our temperatures, okay, our world temperature, but I mean, this is how we keep ourselves warm. This is how we can slowly warm and slowly cool ourselves because of this high heat capacity, okay? I can go outside when it's 100-degree weather there, and I can all of a sudden not melt right away, okay? In about 2 minutes, I'm gonna be sweating my butt off though, right? But it allows us to absorb that heat and have our temperature change slowly over time. And here, sorry, okay, here you can see that, okay? High heat of vaporization right here, which is the next capacity here. But, you know, I don't just all of a sudden just bam, okay? Or I don't just go, whoosh, okay? I don't just skyrocket up, all right? These hydrogen bonds absorb energy before we get a change in state. We absorb a lot of energy before we have a change in state. That's awesome, okay? Water has a high heat of evaporation, and that's what you see right here, okay? It doesn't take much to go from a solid to a liquid, but it takes a hell of a lot of energy to go from a liquid to a gas. Again, that is awesome, all right? That is awesome. I can use this, okay? I can use this to cool me down, okay? I can, you know, that sweat on my surface, sorry, I hit my mic, that sweat on my surface, okay? I can blow on the surface of my skin, and all of a sudden my skin feels cooler, okay? It's taking all that water on the surface, all that sweat, picks up that energy as it gets removed and blown off the surface of your skin, and it cools you down. That's what you see right here in this picture. Elephants don't have, they don't have sweat glands. They don't have sebum glands. Sebum is stuff that gets produced in our skin. Helps to make it all soft and supple. It doesn't look like a pachyderm. Okay? And there's conditions where you have pachydermy-like skin, elephantitis. Okay? So that's why elephants love to splash water on themselves. They love to cover in the mud because that helps to keep their body cool. Okay, and it helps to cool them down. All right. So bodies of organisms cool when their heat is used to evaporate water. So as you get to the surface there and all that sweat, you know, as you kind of move around, all that sweat starts to evaporate and you start to cool down. Number 3, water is a great solvent. Okay. It is what, you know, we use water to dissolve things in. Okay. Why do items dissolve so easily in water? Come on now, polarity, okay? Again, the positive can orientate towards something negative. The negative can orientate towards something positive. So I can dissolve substances very easily by just throwing them in water. I'm sure you've made Kool-Aid before and you've seen this phenomenon, okay? We have substances that can completely dissolve in water, okay? And they're referred to as hydrophilic. What does hydro mean? Hydro means water, okay? And philic means love, okay? So these are substances that are completely dissolving in water because they love to interact with it. Conversely, hydrophobic substances do not dissolve in water, okay? Hydro, again, water. And phobic is fear. The kids are going crazy upstairs. I don't know what the hell's going on. Fear. F-E-A-R. Okay, they fear water, so they repel it. They run away from it. So water is a solvent. You put substance within it. Those substances are referred to as solutes. And you'll see this terminology when you start doing the food molecule lab on Labster. A solution contains both the solvent and the solutes. Okay, the solution is everything. And here you can see salt dissolving. Why? Because that water can break up the bonds in between sodium and chloride. Water can break that ionic bond. And then I can disassociate those two ions so they don't interact with one another. There's my sorry, hydrogen bond. Okay. Okay, there's my hydrogen bonds. So again, it's these hydrogen bonds that were individually so weak and pathetic, but grouped together, they're fantastic. They're awesome. Number 4, it was in the chat box earlier. I can't remember who brought it up, but there it is. Okay. Because of these hydrogen bonds, water molecules are adhesive and cohesive. Okay. What the hell does that mean? Well, cohesion is the ability of water molecules to cling to each other. Okay? That's all it is. Okay. When water starts to run, I mean, you don't get a group of water here and then a group of water here and then a group of water here kind of going in a general direction. They're bonded to one another. All right. If you've ever filled up a cup to the very brim and try to keep going and it kind of has this bubble of water up top and you're like, whoa, what the hell? I'm like a magician or something. Okay. That is due to that cohesion. Okay? Ability of water molecules to cling to one another. Adhesion is the ability of water molecules to cling to the surface. Okay. These two things go hand in hand with one another, adhesion and cohesion. They always kind of go hand in hand with one another. Okay. This, again, is due to that kind of polarity. Okay. That polarity that exists because of those hydrogen bonds. This is how content moves through your capillaries, those small little blood vessels deep in your tissues. All right. Blood, as blood enters in there, it is going to keep going forward because it's, they're all going to line up one at a time and they're going to adhere to that wall, and that wall is going to contract and push and it's going to, they're going to move forward. All right. The other red blood cell that's right on my butt here, it's coming with me because it's attracted to my butt. It's that hydrogen bond. This is how stuff gets way up in a tree as well. This adhesion, cohesion. At the leaf level, we get evaporation, okay, the sucking out of water out of that tree. But we have the roots deep in the ground that's picking up that water. Okay. And it gets to the very top, even though gravity's pulling it down though. What the heck, man? It's those water molecules clinging to one another and clinging to the sides of that xylem and phloem that get that water to go all the way up from the root system all the way up 40 feet in the air and not get pulled back down to the earth. It's that adhesion and cohesion that allows that to do that. That's why trees can get big. The last one we have here is frozen water is less dense than liquid. Okay. Ice floats. Okay. Ice floats. It's less dense. Why is it less dense? Because water is expanding. Those hydrogen bonds start to strengthen or start to get lengthened out a little bit, right? They get lengthened out because this thing, this water, is starting to solidify. Okay? So here you can see kind of these hydrogen bonds here in this liquid are really close to one another. And here you can see they get pushed out. Okay? And that decreases that density and that allows that ice to float on the surface. It allows life to exist in a pond in the winter, even though it's frozen solid. You can walk across it. It is not frozen on the bottom. Okay. So this concept of having less density than liquid is what allows liquid to float and what allows life to exist in water bodies. Again, makes a fantastic short answer question. Okay. The last few things, we'll get to these last few slides here and call it a day. I have a little poll question and some attendance to take, so don't run off. All right. So if your internet falls out, get back in. Okay. So that's water. So the last kind of few concepts when it comes to chemistry here, this concept of acids and bases, okay? And the way we measure the number of hydrogen ions within something is called the pH, okay? And we have the pH scale 0 to 7, or 0 to like this 6.9, 7, and then 7.1 on up is more alkaline or basic, right? You know the pH scale, right? When water reacts with stuff, it ionizes things, okay? It can separate ions out, and water is no different in that regard, okay? When we've gotten a release of hydrogen ions, okay, that is associated with being more acidic. When we get an increase in the number of hydroxide ions, okay, that's more basic alkaline. And I think I have that word on the next slide, so don't freak out if you don't know how to spell it. Okay. Bases either take up hydrogen ions, okay, or they release hydroxide ions. Okay. Again, what does hydrogen have? It has one bond. Okay. It's missing an electron. That's why it's positive. Okay. Here, it's taken that electron. That should be here. Okay. It's got a little extra electron floating around here. Okay. So it's gained that electron that should be here. So it's negative. Okay. Acids and bases are the basis for how, let's see what I did there. It is the hallmark for how you're still alive. It is this concept of pH and the acid-base balance within your body that allows you to eat really spicy food and not tear your stomach up to kingdom come. It allows you to have situations in the body where you have an accumulation of acidic content, like when you exercise pretty heavily, right? And you're able to buffer that, okay? You're able to use this acid-based thing and create these things called buffers, which is on a few slides from now, all right? So this concept of acid and base is the basis for how you're still alive. Here it is. You should probably know these, okay? Okay, you should probably know those. Matching, multiple choice, that'd be the way to do it, okay? And it's based on a logarithmic scale, okay? So every time you go up a number, that is a 10-fold increase, okay? So 8, 9, 10, that's a difference of 100. So that's 100 times. So every time you just go up from one number to the next, that is a 10-fold difference, okay? Go up 2 numbers, that's 100. Go up 3, that's 1,000. We just keep adding a 0. And here you can kind of see, here's around your stomach acid right down here, around a pH of 1 for all intents and purposes, okay? If you're trying to reduce acidity, that's why they, say to drink milk, because it's more towards neutral. Okay. Baking soda, more alkaline, so it's going to decrease acidity. There is a supplement that's based on that baking soda concept, and that's supposed to buffer dramatic pH changes, but there's really not a whole hell of a lot of support for it from a scientific standpoint. For newbies, I think that's probably a good thing that you can do. But for anybody who's trained for any length of time there, those buffers, they're not necessarily all that effective. What the hell is a buffer? A buffer is something that keeps pH within normal levels, okay? You can see our blood is around 7.4, and I may ask this concept question, I may not, all right? But human blood is around 7.4, which is slightly alkaline, slightly basic, and I keep saying alkaline, there it is right there, okay? Alkaline is basic, all right? So it's slightly alkaline. If I take that pH of blood and I screw with it even just a little bit, I'm okay, okay? Like 7.2, 7.6, I can still function normally. But if I get from 7.4 to, whoa, drop it down to way low, 7, Now I'm slightly becoming acidic, all right? And that's referred to as acidosis. Acid, osis just means condition of. Condition of, okay? And it's a condition of the blood, basically. All right. So if that blood pH drops and becomes more acidic, if you don't fix it up in time, that can wreak havoc on a lot of systems inside the body. Same thing if it becomes too alkaline. If it becomes too alkaline, it's referred to as alkalosis. And again, the same thing can happen. Systems start to diminish in function. Your body has this nice little range of homeostasis that it likes to be in. You get too far one way or the other, and stuff just starts to diminish in function. Okay, you can start destroying structures. You can change the enzymatic activity of the brain. You could change the enzymatic reactions that occur within the stomach by altering the pH. Now bacteria can grow in the stomach. Not good. Now you won't be able to free up B12 because you've made it too alkaline in that stomach. And the small intestine can't absorb B12 now. You're like, oh no. Well, B12 makes red blood cells, or helps, one of the things that help make red blood cells normal. So if I don't have effective red blood cells being made, I'm not carrying oxygen. If I'm not carrying oxygen, I can't make a lot of energy. And I'm not making a lot of energy, I can't do crap. And I just sit around like a bump on a log all day long. Because I don't have energy to get up and be active and do stuff, okay? And that can, lead you down a bad path. And that's what you see with a lot of elderly. They have a lot of pH changes within their stomach. And, that's an affliction. Rye gut, pernicious anemia. That's something that you see a lot in older people because of that change in pH that can happen in the elderly. We have a ton of built-in mechanisms to help prevent this, though. Okay? One of them is the carbonic acid buffer system. There are a multitude of them. There's a chloride shift. There's a positive. There's a bunch of them. I'm not going to ask you the name of the carbonic acid buffer system. Okay. I just want you to know that we have a lot of built-in mechanisms in the body to help prevent crap from hitting the fan. That's all I want to say about that. I'm going to share one more thing with you guys here. While I'm doing that, I'm going to start this. Give you a minute to answer this. There's a little poll. Answer it. Okay. I can't see who has taken the poll, so just answer. This type of bond involves the sharing of electrons. Okay. Give you a few more seconds here. How many people? I got 29 people, 28 people, 15, 20, 21. Come on. Find it in your notes. 2 people. Come on. Gotta be faster if you're gonna cheat. Come on. Boom. Nice. The type of bond that involves a sharing is covalent. Nobody went family bonding. Damn. All right. So let me share my screen one last time with you. While I'm doing this, why don't you guys write your name over there in the box? You can make it public. You can make it private. If you're scared to let people know your name, that's fine, because that's how I'm taking attendance. Pull this up. Where's it going? There it is. Okay. While you're doing that, share my screen here. Nope. Share that. So here I am sharing the screen here, and this is on, again, your My Grades, okay? If you click over here on My Grades, there's the due dates right there, okay? For those that love due dates, there you go, okay? I am fulfilling your desires. Don't say I don't do anything for you. Okay. I also made an announcement as well. I kept screwing up. That's why I kept sending it out. So I apologize. It was early. Okay. And there you can see it right there. Same thing. Hey guys, I know we've ended, but I screwed up and I forgot to hit record. So I'm going back to the beginning at the end to get the beginning so the end makes sense. So in the beginning, I was talking about these first couple slides, and there's only like 3 slides, so just bear with me, okay? Matter. What is matter? Everything is matter, okay? Anything that has mass, anything that takes up space, boom, that's matter. And it's the interaction of the stuff inside this matter that is what's going to allow us to figure out how chemical reactions occur, how items are formed, how items are broken down, all that fun stuff. When we look at matter, you know it, 3 different forms: solid, liquid, and gases. And we can go from one form to another when we put in a little bit of energy. The stuff inside matter, and it doesn't matter whether it's living or non-living, but all matter is composed of the same basic substances. And by substances, I mean the elements, okay? Living stuff is generally referred to as organic, and organic has the molecule, has the element, carbon within it. Inorganic substances do not. Non-living substances do not have carbon associated with them. So that's what C stands for here. What are elements? Elements are substances, okay, that cannot be broken down. Okay? If I break down an element into its constituent parts, then it's not the element anymore. Okay? A carbon is made up of even smaller stuff. Okay? And those smaller things are even made up of even smaller things. And if I break up a carbon into its just individual protons, neutrons, electrons, now it's not carbon because I've separated them all out and they're not connected anymore. So they're not going to have the properties that all of them put together do have, carbon. We have 92 elements that are naturally occurring, but really we're only worried about 6, okay? And I would know the 6. Okay, they make great, maybe multiple choice question. Okay, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And those are the 6 elements that, are the vast majority of us. But as you can see, I mean, there's a lot of other elements. There's a lot of other stuff that is within us. Calcium, iron. There's iron in the crust and there's iron within us. There's more within the earth though. Potassium, sulfur, phosphorus, silicon, aluminum, magnesium, sodium. You can see all of these constitute both us and the earth. It's just that, one's a little bit more in one than the other. You need iron to survive. Okay? If you don't get enough iron, you don't make enough red blood cells. When it comes to these elements, they are made up of even smaller stuff called atoms. And these guys all together will share the same name, okay? The atoms inside the element all are reacting the same, all have the same name. I don't just say these are the protons of the carbon atom, or these are the protons, or these are the neutrons or electrons. Nah, and elements and its atoms all share the same name, all right? These 3 specific subatomic particles that I would like you to know are called the proton, the neutron, and the electron. 2 of them are found specifically in the nucleus here that I have circled. Again, protons and neutrons. So they're within the center right here. Protons are positively charged. P of proton, P of positive. Okay. Neutrons are neutral. They don't have a charge. N of neutron, N of neutral, or N of no charge. Floating around that center, that nucleus, that center-like nucleus structure, are the electrons. Electrons are negative. As you can kind of see, I have an associated amount they weigh. I'm not going to ask that. Okay? Protons and neutrons both have mass to them. It's called the atomic mass unit. That's AMU. Electrons, really, they're really low. And so they're negligible in calculations, all right? But I'm not going to ask you how to calculate, or I'm not going to ask you to calculate atomic mass units on the exam. Now, I'm going to ask you what the atomic mass number is, okay, or what that equals to, or what the atomic number equals to, or mass number equals to, but I'm not going to have a calculation for you to figure that out. That's beyond the scope of the class, okay? But knowing protons are positively charged, electrons are negatively charged, that's something to remember, and neutrons have no charge, they're neutral. Okay. And here you can kind of see right there, positive, negative, no charge, where they're located, where they're at within the orbit, or what's called an electron shell, which is this thing here. Okay, this thing here, that circle, which I can't draw a circle. Right. And I believe this is where we start our journey when I hit the record button. So I apologize for not getting that done earlier, but hopefully you don't hate me too much. Okay? You guys have a fantastic weekend, and I will see you next week.